Okay, last lesson of the unit, exponential equations and changing bases. So you viewed the video already on the change of base theorem. So if our base is not 10, which would make it the common log, or e, which would make it the natural log, then we can change the base to be whatever number we want. If we're using our calculator, it just makes sense, though, to either change it to the common log or change it to the natural log. So the one thing that I need to remind you of, the base of the logarithm has to be the number that's in the denominator. Okay, so it's the log of the expression divided by the log of the base, regardless of what you're changing the base to. All right, let's go through some solving. So give exact answers here. So x cubed, not an exponential equation. What do? I take the cube root of both sides. So x is equal to the cube root of 81. Okay, this is not 3, right? Because 3 cubed is equal to 27. So we just keep it as such. Now, we could, now that I say that, we can break this up as 27 times 3. Okay, so 27 times 3 would give us 8. And now when I look to take the cube root of each of those factors, so my exact answer would be 3 times the cube root of 3. Okay, next, this is an exponential equation because now my exponent is the unknown. So I change to the bases that I know. So 81 is 3 to the 4th power. So x is equal to 4. Now you may not necessarily need to write this step, and that's fine. All right, we've looked at a lot of these problems. All right, and then lastly, again, not an exponential. I'm solving for x. It's a polynomial, so I'm going to take the 4th root of both sides. And then let's remind ourselves, when we take an even root, 2 answers exist. I can't simplify the 4th root of 8 at all because 1 to the 4th power is 1, and then 2 to the 4th power is 16. So there's no factors of 8 that I can take the 4th root of. Okay, now here, when I'm looking to solve, both of these are exponential because they're both in the form where the exponent is the unknown. So how do we solve an exponential? We write it using logarithms. So I can write this, log base 4 of 81 is equal to x. And now that my base is not 10 or e, now I use my change of base theorem. So in my calculator, I could set it up as the log of 81 divided by the log of 4. Now I do ask you for exact answers, so you just leave it in terms of a log. If you prefer to use the natural log, we've seen several times that these are exactly equivalent. So whether I take the log of 81 divided by the log of 4, or I take the natural log of 81 divided by the natural log of 4, then I'm good. All right, my next one, exponential, I'm going to write it as a logarithm. So log base 10 of 3 would equal x. Log base 10 is my common log. So log of 3 would just be the exact answer. You don't need a change of base theorem because the base is 10. Okay, let's look at another example of how to solve these. So I just showed you exponential. I write them as a logarithm. Log base e, that's the natural log. So using my calculator, ln of 12 would give me about 485. Oh, hundredths. Okay, now another method that you could use, so I like you to rewrite it as a logarithm because we kept talking about the logs and exponential functions being inverses of each other. I can also, it's an equation, so I can take the log of both sides. Okay, so it's still using the fact that we know logarithms and exponential functions are inverses of each other. But now if I just take the log of both sides, now I can use my rule where I can bring my exponent out front of the logarithm. Log base e is the natural log. ln of e, we talked about this in class the other day, that's 1. So when I look at this in my calculator, plug this in my calculator, I got 1.08. So let me go back here. Here's my mistake. The log of e, so this is already base 10. So my mistake was saying that the log base e is natural log. Well, that's true, but the log of e, they don't cancel each other out. So I have to come back to this. This stays log of e. So now when I solve for x, I would then have to take log of 12 and divide it by log of e. And now on my calculator, log of 12 divided by log of e. That gives me the same answer. Right? So regardless of the method, we better be getting the same answer. So I knew I had made a mistake somewhere because I wasn't getting the same value. Again, log of e is log base 10 of e. Log base e, that's my natural log. Okay, so they're two separate things. So either method, you can go right to exponential form and then use a change of base, or you can introduce the logarithm on both sides and then use our casting rule to bring our exponent out front. So let's practice this one here. So I'm going to take the log of both sides. I'm going to use my exponent rule. And then to get x alone, I'm going to divide by log of 3. Now, when I go to plug this in my calculator, log of negative 11 divided by log of 3, I get a domain error. I get a non-real answer. So let me remind you, for our logarithmic functions, okay, here, log base b of x equals a, our domain are all positive values. So I can't take the log of 0, I can't take the log of a negative number. On a calculator, it'll give us no solution, so don't be thinking that you did something wrong. The error is here in the domain. All right, suppose you invest P dollars at an annual rate of 6%. How long will it take to double your money if your investment is compounded annually? Okay, so initial investment, 1 plus my rate to the t power. If I want to double my investment, then whatever my initial investment is, to double it would be 2p. All right, dividing both sides by p, I get 2 is equal to 1.06 to the t power. Now, when we started this at the beginning of the unit, the question was between what 2 years would this be true? So now we have the means to solve it directly. So log base 1.06 of 2, that'll give me t. That's writing my exponential in logarithmic form. Using my change of base, if I take the natural log of 2 divided by the natural log of 1.06, this gives me 11.89, so about 12 years to double my investment. Or if I wanted to take, now taking the log of both sides, I could also use the natural log of both sides. It does not matter, because we've shown again and again that change of base to natural log or common log gives us the same answer. So I can bring my exponent out front. And now solving for t, notice what we have. You have the exact same relationship, whether you wrote it as a logarithmic equation and used the change of base, or if you took the log of both sides and then used your casting rule. So about 12 years it would take to double my investment. All right, so now what if it is compounded continuously? So our continuous, that was our PERT formula. So I'm still looking to double. So 2p equals PE. My rate, 0.06. My time is what I'm looking for. When I divide both sides by P, I get 2 is equal to E to the 0.06t. My first method, if I write it as a logarithmic equation, I have log base E of 0.06 times t equals 2. No, that's not right at all. I have log base E of 2 equals 0.06t. On the left-hand side, log base E is natural log. So to get my value of t, I take the natural log of 2, and I'm going to divide both sides by 0.06. So now this decimal comes out to 11.6, so it's still about 12 years. All right, and let me just look at the second method. I have 2 equals e to the 0.06t. If I take the log of both sides, all right, bring my exponent out front, so I have a log of 2 equals 0.06t times the log of e. Okay, don't make the same mistake I did. Log of e is not natural log. Now to get t alone, I have to divide by 0.06 times the log of e. So if you're using your calculator, make sure that whole thing goes in a set of parentheses. Divided by... and it does verify that we get the same answer. So 11.6, so 12 years would be my answer. All right, like we talk about constantly. It's 2 methods to do the same thing. All right, so pick one method and do it really well all the time. I won't be looking for one over the other. All right, your homework, page 205, numbers 1 through 14, all, and this can be found in your general tab. Files, and your textbook pages with the rest of the documents. All right, thank you.